Welcome to this comprehensive guide on tree and graph data structures. These are fundamental data structures used in computer science to organize and manage complex relationships. Trees and graphs are essential tools for solving many real-world problems in areas like networking, databases, and social media. In this series, we will explore the key concepts, differences, and practical applications of both trees and graphs. A tree is a nonlinear hierarchical data structure that consists of nodes connected by edges with exactly one path between any two nodes. Trees have several important characteristics. First, every tree has a root node, which is the starting point with no parent. Nodes are organized in a parent-child relationship, where each parent can have multiple children. Leaf nodes are the terminal nodes that have no children. And crucially, trees are acyclic, meaning they contain no loops, ensuring there is always a unique path between any two nodes. A graph is a nonlinear data structure consisting of vertices, also called nodes, and edges that can form multiple paths between any two vertices. Unlike trees, graphs are much more flexible. Vertices are the data-holding nodes in the network. Edges are connections between any two vertices. Graphs can be cyclic, meaning they can contain loops and cycles. Most importantly, graphs can have multiple paths between vertices, which makes them ideal for representing complex networks and relationships. Let me highlight the key differences between trees and graphs. Trees are acyclic, meaning they have no cycles or loops, while graphs can contain cycles. Trees are hierarchical with one root node, whereas graphs are network-based with no required root node. In a tree, there is only one single path between any two nodes, but in a graph, there can be multiple paths. Each node in a tree has one parent, but in a graph, nodes can have many parents. Finally, for n nodes, a tree always has exactly n-1 edges, while a graph can have any number of edges. To visit all nodes in a tree or graph, we use traversal methods. For trees, we have four main traversals. Preorder visits the root first, then the left subtree, then the right subtree. Inorder visits the left subtree, then the root, then the right subtree. Postorder visits the left subtree, then the right subtree, then the root. And level order visits nodes level by level from top to bottom. For graphs, we primarily use two traversal methods. Depth-first search, or DFS, explores deep into branches first using a stack. Breadth-first search, or BFS, explores level by level using a queue. We also have specialized algorithms like Dijkstra for finding shortest paths and topological sort for directed acyclic graphs. Let us dive deeper into the two primary graph traversal algorithms. Depth-first search, abbreviated as DFS, explores by going as deep as possible into branches first. It uses a stack data structure with last-in first-out behavior. DFS is useful for topological sorting and cycle detection. Since it explores deeply, it can use significant memory with potentially deep recursion stacks. However, it has a time complexity of O of V plus E, where V is vertices and E is edges. Breadth-first search, abbreviated as BFS, explores level by level, visiting nodes systematically. It uses a queue data structure with first-in first-out behavior. BFS is ideal for finding shortest paths and recommendation systems. It requires memory to hold entire levels in the queue. BFS also has a time complexity of O of V plus E, making it equivalent to DFS in terms of time complexity. For binary trees, there are three main depth-first traversal approaches. Inorder traversal visits the left subtree, then the root, then the right subtree. This is commonly used with binary search trees to get sorted output. Preorder traversal visits the root first, then the left subtree, then the right subtree. This is useful for creating a copy of the tree. Postorder traversal visits the left subtree, then the right subtree, then the root last. This is particularly useful when deleting a tree. There is also level order traversal, which is a breadth-first approach that visits nodes level by level from left to right. All of these traversals have a time complexity of O of n, where n is the total number of nodes, because we visit each node exactly once. Trees and graphs have numerous real-world applications. Trees are used in file systems to create hierarchical directory structures on computers. They are used in database indexing through binary search trees for efficient data retrieval. Trees represent the Document Object Model, or DOM, in web browsers, and they are used to represent family relationships in genealogy applications. Graphs, on the other hand, are used in GPS navigation systems to find the shortest routes using algorithms like Dijkstra. They power social networks by representing friend connections and recommendation systems. Graphs represent hyperlinks between web pages for web crawling and search engines, and they model electrical circuits and connections in electronic systems. Understanding the performance characteristics of different operations is crucial. For tree operations, traversal takes O of n time, where n is the number of nodes, and O of h space, where h is the height. Searching in a binary search tree takes O of log n time and O of 1 space. Inserting and deleting also take O of log n time with O of 1 space. For graph operations, both DFS and BFS take O of v plus e time, where v is the number of vertices and e is the number of edges, with O of v space. Dijkstra's algorithm for shortest paths takes O of v plus e log v time with O of v space. Topological sorting takes O of v plus e time with O of v space. And cycle detection also takes O of v plus e time with O of v space. Let us summarize the key points about trees and graphs. Trees are hierarchical structures with one root node and parent-child relationships organized in an acyclic manner, with n-1 edges for n nodes. Trees support multiple traversal orders including preorder, inorder, postorder, and level order. Trees are used for file systems, database indexing, and representing hierarchies. Graphs are network structures with vertices and flexible edges that can form cycles with multiple paths between nodes. Graphs support two main traversals: depth-first search for deep exploration and breadth-first search for level-by-level exploration. Graphs are used for GPS navigation, social networks, web links, and circuit networks. Both data structures are fundamental to computer science, and choosing between them depends on your specific data relationships and requirements.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.